My name is Kenneth. I'm a postdoc under Dr. Yangliu in the Department of Dynamics and Control Laboratory, University of Exeter, and we're presenting our study on an AI-assisted biomedical tissue evaluation for the purpose of early bowel cancer diagnosis using the robotic capsule. And this is an outline of the talk I will be giving this afternoon. And as the first part of the talk, I'd like to say something about the bowel cancer. The bowel of women are often characterized with lesions. Some of these lesions can be benign, that is, they have no effect, while at times they can mutate to become malignant, which are can be of health effect or health problem. And we can see that as they mutate, they develop through different stages. These are the stages to which it can go through, starting from the early stages to the later stages when they rupture and begin to metastasize and move to other parts of the body. And presently, bowel cancer stands as the second most deadly cancer after lung cancer in the UK and in the Europe. And there have been studies that try to make sure that this mortality rate is reduced to improve cancer survival rate. And some of those studies have pointed out at early cancer diagnosis, that is the possibility of diagnosing the bowel cancer at the early stage, especially maybe let's say the stage zero, the zero stage. And if we look at the presently existing endoscopy and capsule endoscopies, they make use of visual investigation. And this visual investigation tends to use late-stage development features, such as size, shape, and numbers. And this makes this method not able to detect the bowel cancer at the early stage, thus restricting the possibility of improving the cancer survival rate. In our current work, we are trying to make use of the self-propelled capsule, which has already been introduced by PI, that's Dr. Yangliu. We won't be going through the modality of the capsule. This is just the capsule showing how it moves. But, we have the excitational force that drives this from the outside, and we have the different parameters that can be changed in order to the movement of the capsule, and we have the capsule dynamics, which are the including the capsule displacement, accelerations, and velocity that can be estimated from the capsule equation of motion. And one of my concern being machine learning problem is to be able to simulate data that can be used to train the model, the different models that of machine learning. And in operating the capsule can be operated in two modes, like Dr. Leung has already said about it. You can operate it in such a way it can move forward or it can move backward. And also they can move in the purpose of cancer diagnosis. You can be able to operate it in diagnostic mode, and you can be able to operate it in translation mode. In diagnostic mode, you are able to stick the capsule to a lesions in the bowel, and you allow the capsule to vibrate on it without moving over the lesions, without moving over the constraint, which are called a form of biomedical constraint. And in translational move, you can change the parameters to be able to make the capsule to move over the constraint and continue to move forward in the bowel while you do your investigation. So one of my first step was to be able to diagnose those parameter ranges in which this capsule can be able to remain in the diagnostic mode that is stick to the lesions without crossing over it. And these are some of the ranges that I've seen based on during the duty cycle and the period of the excitation force. And this is the layout of my method, and the proposed method is a simple one in which we have the capsule sticking to the lesions, which is like a biomedical constraint now, and then vibrating on it. And from that, we're able to collect some dynamic variables in terms of displacement. In this case, we're using displacement. And then I'm able to I can feed those variables directly to develop a AI model by training, and also can go ahead and extract some useful features from those dynamic variables instead of feeding the variables that have been mentioned to the models to develop models. And also, even after doing feature extraction, I can also do a sort of feature selection in which I try to kind of reduce the dimensionality of my features to SIP one, and also use them to develop AI models that are able to predict the type of lesions or the type of cancer that we have in that place, that the constraint, which kind of cancer that very constraint represents, either be a early stage or late stage. And this is our experimental setup, which has also been spoken about. We have the coil, we have the capsule that is being driven and vibrated on the capsule. This is a video showing what we did in the laboratory. You can see the capsule moving forward and then sticking to the synthetic lesions that we will develop in the lab and see vibrating on it. And we have the laser that is already is on it that's able to collect the displacement reading. This is a typical example of a displacement signal that's collected from the capsule during the simulation, and this represents one that's collected during the experiment. For the purpose of using the simulated signals, I try to adapt into the experimental form by adding white Gaussian noise of signal to noise ratio of about 20, and then smoothing it just the way I will process the experimental data. And also for the data labeling, I stimulate the strain, that is the the cancer cell tissue that is placed in front of that the capsule is being vibrated, and I try to simulate their young modulus between 12 and 170 PA, and I try to label those that are lesser than 39.6 as the normal tissue, which I term 0, and the other labeling are as follows. So in total, I have 5 classes of cancer lesions that I'm going to characterize. In the experimental format, we couldn't be able to get as many lesion classes like we have in the simulation. We could only get a lesion that fall within the young modulus of the E1 and 2 and 4 class. And in whole, these are the data that were developed for simulation and experiment. And during the, I try to make sure that I use 70% of my data for the network training and 30% for testing the network, which are like out of sample data to actually validate how your network is performing. This is just a distribution of my data, the simulated data and the experimental data, both for the training and testing. And you can see that there's no bias in the way I have divided the data for the purpose of training and testing. For the feature extraction, we did it, about 43 features were extracted from each signal, and we have the statistical features that were estimated from the time domain signal. Also, when we convert the signal to frequency domain, we also extract some features, and also the waveform features. The waveform features refer to just looking at the wave, the signal, and be able to look at some features that you can actually see, especially like maybe let's say the forward displacement, maybe the prominence or the amplitude or the area that is defined under the curve. Those are some of the waveform features I was able to define, and also I have some nonlinear features that were also extracted. So in all, we have about 43 features. And I try to investigate how these features vary with the young modulus of the constraint that is ahead of the capsule. And one of the things I found out is that some at the lower young modulus, you see that the difference between some of the estimated features, the difference between them are a bit wider. But when the stiffness begin to increase, you see that the difference is not, there's no more differences between the estimated value of each of the features. And another thing we find out is that for different operating parameter of the capsule, the feature that is calculated for each of them tends to be different, vary. For example, this is about 18 Pascal stiffness that was estimated for when the capsule is operated with a 20 millimeter amplitude. And you can see for the same, you can see what we have it around 7.2 here, but for the same, we have it around 7.4 here. And for the same, we are having it around 7.8 here. This shows that the operating parameter of the capsule has effect on whatever the features that we're extracting. And what this tells you is that during the process of machine learning, these operating parameters have to also form input into the features you use in training your model, so your model can be able to learn very well. So I can be able to produce a very good model. And also this for the machine learning, we carried out supervised and non-supervised learning. For the supervised learning, I made use of stack ensemble model. Stack ensemble model means you train different types of networks and you try to use them to make prediction, and you extract their score on the data to be as input data. In other words, I'm not actually using the original data as input, but the scores that each of this network produce for each of those data is what I use to produce new network. And then we also made use of the multi-spectrum layer, which are just simple network. In this case, I use a tool after some comparison with 2 layers and different number of neurons. I resolve into using 2-layer multi-spectrum with 3 neuron. And this is the result of the simulated data using the ensemble models, the ensemble network model. One of the things you can see is that I try to compare the results for when we use the raw data, that is the raw displacement data as we are getting it from the measurement, either simulation or the experiment, though after some normalization, because you have to normalize, but that's still the raw data. And also the features, the 43 features that I have, I also use them to develop network model. And also I carried out some sort of features reduction, dimensionality reduction of the features using different feature reduction models, and then compare the results with what we have. As you can see, for the ensemble network, we see the network actually perform well with the raw data, because that's about on the test data. So on the test, the red one and the test data, the black one and the when the training. On the test, I can see that the ensemble network perform well on the raw data, even without forming any feature extraction on the raw data. And so also where when you use the whole feature. One of the on the average, you can see that the ensemble network has a accuracy of about 91.7% accuracy. And we can also see that the stack ensemble that is combining all the ensemble network is more better than each of the individual network. For example, we have the SVN having an accuracy of 93% here, but when you have the stack ensemble, it was able to obtain up to 95.9% accuracy. So those are some of the things we found out. We also found out that the SVN network on its own also performed well, because if you look at it on the average, about 5 features that were used, that's 5 models now, 5 of them were able to produce accuracy that is greater than 90%. So also the stack ensemble network, but for all that network, it's that the only one who was able to achieve an accuracy that is greater than 90%. For the ML model, we have this, and we also using the raw data, we can see that the ML model does not do well when you use just the raw data to make the prediction to your network. But when you extract features, you can see that the accuracy improved from 87.5 to 97.8 for the testing data. And that's for the simulation data. And for the experimental data as well, we also see the same trend in which the network perform better on feature-based model. And on the average, you have the network giving about 96% accuracy for the simulation and experimental data. This is a typical example of what we have predicted classes and on the test data. And if you look at it for each of the class, we can see that the misclassified data are at the edge, like at the boundary between where you have this with each of the class is at the boundary. It's not like in between, so it's just at the boundary. And this is because the spacing between the young models we're using are very small. That's just the difference of 1.2 kpi that we're using. We didn't allow really, we say continuous simulation, so that's why it found it a bit difficult at the edge to be at the boundary to be able to make this prediction, which we expected. For the unsupervised classification, we try to use k-means clustering. At first, I tried to calibrate to cluster for into 5 classes like we did for supervised learning, but it was not possible. As you can see in a category, we see that network is categorizing it's a single category to about 3 classes, which is not what we want. And that's why we have to reduce it to 2-class classification for the k-means clustering. By unsupervised learning, I mean we are not supplying the networks with the labels like the supervised, where we supply the network with the labels. But for this unsupervised, we are not supplying the network with the label. We just do the clustering of the features to see what classes we have. So for the E1, we name it as a normal tissue, while from the E1 to E4, we name it as a category 2, which is the cancerous tissue or malignant tissue. This is the result of the 2-class clustering, which we cluster the data into those ones that are normal and those ones that are already cancerous, using different model of k-means constraint. And what we found out is that the squared Euclidean distance give better performances when we are doing this, both for the simulated data and both for the experimental data. And in the misclassified as well, we can see that it's at the boundary, at the edge. That's where the network is finding it difficult to classify. And so in the conclusion, I can say that the stack ensemble network has better performance when you are using raw data for supervised classification, while for single network classification, the MLP and the SDM, that is support vector machine, are preferable for that classification. And I can say that unsupervised, for the purpose of unsupervised classification, it is better to classify the cancer cell into two classes, that is the malignant one and the normal tissue. And then we found out that feature selection did not actually improve the performance of the network, but it does really reduce the time taken for the network to actually train. In future, what I decided to do is first to establish which of these features, because right now we have not established, because still need more experiments, still need to carry out more experiments to establish which of these features actually have the best correlation with the biomedical properties of the constraint of the tissue. And also we want to establish a benchmark between the LD tissue and the early stage cancerous tissues based on their Young modulus. We have to have a benchmark that differentiates between them, which we have yet to establish. And we also further investigate other methods of unsupervised classification. And also, we also want to carry out in vivo testing of this present method. And my present study was sponsored by the EPSRC under the New Horizons project. And the title of the project is When a Microrobot Encounters a Bowel Lesions. And we also have a collaboration with the Royal Devon University Healthcare here in Exeter. Thank you.